All right, I'm going to do a little supplemental screencast here on modern physics. There were some questions I think you guys had on your homework assignments that you've been doing for AP Classroom based on the videos that were done by the College Board, which are kind of overviews. They don't have a lot of detail, so I'll try to fill in some of the gaps on some of the topics to get you ready for a quiz on Monday. And the topics I'm going to talk about in this screencast are quantized energy, what that means, quantized energy, like little packets of energy, which are photons. Then we'll talk about the photoelectric effect, which is the virtual lab that some of you were able to do, but not everybody. So I want to make sure you guys understand how the photoelectric effect works, what it's all about. Then I'll talk about atomic physics, energy level diagrams, and how the Bohr model of the atom explains spectral lines and some other phenomena. So hopefully it's not too long. I'm going to try to be as efficient as possible as I talk through these things. Okay, moving on to the first topic, quantized energy. So quantized energy, a quantum is like a packet. It's like a little discrete packet of something. And Einstein was the first guy to pose the idea that light came in little packets called photons, which is a discrete portion of electromagnetic radiation that has energy, but I'll say, but no mass. So it's like a light particle without mass, but it's just a little packet of energy, which is kind of hard to picture. But the amount of energy in a single photon is equal to this little equation right here. The energy of a photon is equal to a constant h times the frequency of the photon. And you might have seen this in your reading. This constant is called Planck's constant, after a German physicist, Max Planck. And it's a very famous number, 6.63 times 10 to the negative 34. This equation is kind of like the Newton's second law equation of modern physics. So this is the really the key equation if you're talking about amount of energy in a photon, especially as it applies to the photoelectric effect. All you have to do is know the frequency or even the wavelength of the photon, because then you can calculate frequency. And then you can calculate the energy if you have Planck's constant, which is a number that's on your equation sheet. Very, very small number, 10 to the negative 34th. All right, so that's a really small number. But you remember the frequencies of electromagnetic radiation can be really high, on the order of 10 to the 14th, 15th, 16th hertz, which is in the visible light spectrum in there. And combined with this equation here, which is just the wave equation, where velocity is replaced by c, the speed of light, because all electromagnetic radiation moves at the speed of light. You can, if you know the wavelength, you can solve for frequency, or you can just substitute in for frequency here, since frequency is equal to speed of light over wavelength. I can substitute in that, and I could have hc over lambda. So if you know wavelength, you can also solve for energy. All right, so that's an important relationship to know as we talk about the photoelectric effect. So what is the photoelectric effect? Basically what was discovered in exploring, really tiny things, which is part of what was happening in the early 1900s. They were trying to understand the elemental building blocks of matter. And they were doing all kinds of crazy experiments. And one of them was to take a cathode, which is just a piece of metal that's got a negative charge on it. So this is a variable potential source here. Variable meaning I can adjust the amount of voltage between the two terminals. So it's like a battery that's adjustable. So I have a negative terminal and I have a positive side to this. So I've got a little piece of metal. It could be any kind of metal. You saw in your experiment maybe there was sodium was one of the metals. You could have iron. You could have any of the metals on the periodic table as this plate over here. The anode's the positive side. So basically they're different potentials. And when you shine some light, some electromagnetic radiation on the negative side, there was a current that would come through here sometimes. There would be a current through the ammeter. This is an ammeter. And they'd see a current through the circuit, even though there was no connection between the cathode and the anode in here. It was just kind of wide open. So now they're trying to explain that. What was happening is that some light, no matter how intense it was, intensity is brightness. So no matter how intense the light was, you wouldn't get any current. But with other types of light, different wavelengths, you got a current even with low intensity. And they're trying to figure out how to explain this. Okay, so they're trying to use the electromagnetic wave model to explain it, but there were several aspects of this experiment that the wave model would not explain. Here are some of the things where the wave model fell short. The stopping potential. The stopping potential is reversing the voltage. So you'd see some electrons being liberated on the negative side, and they would travel across empty space or the low pressure gas in there to the positive terminal to complete that circuit and allow current to flow. Well, stopping potential is changing the voltage on the battery, reversing it so that it would stop the current flowing through there. So even though you were liberating electrons, you were changing the potential across there so that they wouldn't make their way across the empty space there. And it didn't depend on the intensity of the light. So the current didn't, and the stopping potential didn't depend on how bright the light was. The fact that there was this thing called a cutoff frequency. Remember, frequency and wavelength are related. So there was a certain frequency or a certain wavelength of light where there was no photocurrent. No matter how intense you made the light, there is a certain frequency where if you got a lower frequency than that, you wouldn't get any current at all. So that was really unusual because in the classical model of physics, intensity is dependent upon amplitude, and amplitude is equal to energy of the wave. So this didn't make any sense because you would seem like the more intense, the more energetic the wave, that should liberate more electrons, and that wasn't what was happening. The last item is there would be an immediate photocurrent when the electromagnetic radiation, when the light first struck the cathode, even for low intensity for certain frequencies. So certain frequencies at low intensity allowed a current to start flowing right away. So it seemed like what was being shown is that the photocurrent was dependent on frequency. Seems like it was dependent on frequency. And that's exactly what they found. Okay, so here comes Einstein, and he develops this equation right here. And he says, hey, this work function right here, phi, this work function phi was equal to the minimum frequency of electromagnetic radiation, let's just say light, the minimum frequency of light times the Planck constant that would liberate electrons. So regardless of intensity, regardless of how bright the light was, there's a minimum frequency which would, and remember this is equal to energy. So this work function is basically measured in joules. It's just energy in joules. Actually, it's measured in electron volts because we need some small units. So you know how to convert joules to electron volts, I think, from earlier in the year. But it turns out that this was the minimum amount of energy needed to liberate an electron. So this relationship right here says this is a fixed frequency right here. This f right here is variable. That's a variable f. So you've got this fixed amount of energy to liberate electrons, the threshold, let's call it, the threshold energy to liberate electrons. Then you might strike that cathode with a higher energy electron. That's this frequency right here, and that's going to give you the kinetic energy of the ejected electrons. This is the kinetic energy of ejected electrons. I'm going to put that in the form of a graph for you, and I think it's going to make some sense, I hope. Okay, so here's a graph, and I think this will help explain that equation. Remember, the equation looked like this. I'm going to write it a little bit differently. K of the electron is equal to HF, like that. Okay, well, think about this equation for a line. Okay, and then I'm going to say what we have on the y-axis is the kinetic energy of the ejected electron. My x variable is the frequency of light that strikes the cathode. My slope is actually going to be the Planck constant. My y-intercept is going to be the work function. What does that look like? It's going to look something like this. It's going to be a linear graph. My slope is a Planck constant. My y-intercept down here is a work function. And what this tells you is this is the cutoff frequency, or the threshold frequency, at which there has to be a minimum frequency right here to get an electron to be ejected. So if I have just that frequency, the ejected electron doesn't have hardly any kinetic energy. As I increase the frequency on the x-axis, the ejected electron ends up having more energy. Okay, it increases. So that's up here in this equation. As I increase the frequency of light that strikes a cathode, multiply it by h, that gives me the energy of that photon that's striking the cathode. Subtract the work function, the minimum energy required to be able to get an electron out, and what's left over ends up being kinetic energy of the ejected electron. Okay, so that's this is a graph that if you took the y-intercept, there's actually no points along this right here because you don't get any, you can't have a electron with negative kinetic energy. But if you were to extend that line down here, the y-intercept would be the work function. So I hope that helps you understand how the photoelectric effect works and how it depends on the frequency of light that strikes the cathode. Notice the higher the frequency, the higher the energy of the ejected electron. So let me just write that down here. As frequency increases, the energy of the ejected electron increases. So what kinds of light have higher frequencies? The UV spectrum has a higher frequency. The shorter, so ultraviolet, and that's shorter than 400 nanometers. Even the shorter wavelengths of light, like the violet wavelengths, they have shorter wavelengths, higher frequencies. They will eject electrons with more energy than the longer wavelengths in the red spectrum. And how does the intensity affect that? Intensity, the more intense the light, the more photons. Brighter light, more photons, and that's associated with more ejected electrons. So the current will go up, but they won't have any more energy. There'll just be more electrons at that same energy level with a higher intensity of light. Okay, hope that makes sense to you. Let's move on to the next topic that I talked about at the beginning, and that is atomic physics and the emission and absorption of photons, basically energy level diagrams. So these are energy level diagrams. And excuse me, energy level diagrams are created to kind of graphically show the energy of electrons in their orbital shells in the Bohr model of the atom. So the Bohr model of the atom basically states, as it was on the AP College Board lectures, that electrons exist in discrete shells around the nucleus. They don't really orbit. They're kind of in a cloud in that shell. The probability of them being at any one location in that orbit is really based on statistics. But the closer they are to the nucleus, the more stable they are. So the closest shell to the nucleus is called the ground state. It's the least energetic state, and it requires the most energy to liberate that electron because it's closest to the protons. It's closest to the nucleus. That Coulomb attraction, that Coulomb force is really strong. So to get that electron out of that inner shell is very difficult. So this is a hydrogen atom or a hydrogen-like ion with a single electron and a single proton. So here's the ground state, we'll call this. That's the least excited state, and it's closest to the nucleus. Then the next shell up is way up here, and this is the first excited state. So it's the next shell up from the ground state. And in order for an electron to jump from the ground state to the first excited state, it has to absorb a photon. This wavy little arrow is the symbol for a photon. So it comes in, it has to have exactly the right energy that matches this jump from this. This is a discrete jump from here to here. if you notice, this is about negative 13.6 electron volts right here, and this is about 3.2 electron volts right here. So it would have to, negative 3.2, would have to be a 10.4 electron volt photon. So this has to be 10.4 eV, and divide by the Planck constant, and you'll get the frequency of that photon. So there's a very specific wavelength frequency of photon that needs to be absorbed by that atom in order to make that specific jump. Likewise, if the electron falls, if it goes from the first excited state down to its ground state, it's going to emit a photon. Notice how the arrow is going this way. It's going to emit a photon. So there are specific wavelengths and frequencies of photons that can be absorbed or emitted for any given element. Okay, so you'll notice here for this hydrogen-like ion, you could have a jump from the fourth to the third quantum number, which would be the third excited state to the second excited state to the first. I could go from the first down to the ground state, or I could have one that jumps all the way down here and skips this level. So there's all kinds of combinations of photons that can be emitted or absorbed based on jumps between those energy levels. So you can skip energy levels in the jumps. And that's kind of shown right here. This is a hydrogen-like ion, either hydrogen or helium or lithium that's ionized once or twice. So it's anything with a single electron. It would have the same structure here, or same energy level diagram. And some components of the energy level, some characteristics of the energy level diagram you should be aware of. The energy levels are on the left-hand side. They're all negative because that means it requires energy to liberate the electron. So to get this electron completely out of the atom, that's negative 13.6 eV. You'd have to have a photon with at least 13.6 electron volts to liberate an electron from the ground state in the hydrogen atom. So if you have a 14 eV energy photon, that could liberate the electron with a little bit of extra kinetic energy. But electrons jumping within these energy levels, they emit and absorb discrete frequencies and wavelengths of light. And so every single element has its own signature. So you see hydrogen right here, we were just talking about. These are the wavelengths of light emitted by hydrogen when an electron jumps from one level to another. And in this case, since a photon is being emitted, the jump would be from a higher energy level to a lower energy level, and that's the emitted photon. So these are emission spectra at these different wavelengths. This is the coolest lab I think we do all year. We actually have a setup where you can look through a spectrometer and see these wavelengths as we have vacuum tubes filled with hydrogen and helium. You can actually see these bright wavelengths of light. I'm really bummed that we can't do that. So that's unfortunate because it's a really cool lab to do. And the lab is actually where I give you an unknown element and you check out the spectra of that element, and then you identify what that element is based on searching the internet for something that matches that signature. So that's actually how we tell what elements are in stars. We analyze the starlight this way. So hopefully that helps you understand what spectral analysis is and emission and absorption spectra. The last little thing here, there's a question, a free response question about getting, light was incident upon a mirror in one of your assignments, and the mirror was sliding along a frictionless track. And the question asks, how does that happen? What causes that? Paragraph length response, I think. Actually, photons have momentum. Believe it or not, photons have momentum. And it's not momentum because of mass. It's momentum that is expressed this way. And there's a whole derivation to show where that momentum or this equation comes from. It's not a long one. It's a pretty simple derivation, actually, but I don't want to go through the time to show you that. I just wanted to give you a basis to understand why the mirror would move, and actually it would move very, very slightly. It'd have to be really high frequency, energetic light that would with very, very, very short wavelengths, right? Short wavelengths means high frequency, so ultraviolet, maybe X-rays, gamma rays kind of thing, so that it would actually have very high momentum and be able to move, something with mass. All right, so I hope that helps you understand a little bit about modern physics. We'll have a quiz on Monday. I'll send you some notes. I'll send you a little update on Schoology to give you an idea of the context of the quiz. Okay? Have a good weekend and be safe. Stay healthy.